So today we will continue talking about dynamic programming, and today we will be talking about knapsack problem. What this problem is about, you are given a lot of items with weights, n, so you have n items with weights, and you have a backpack with their capacity of W large. So, and the problem is on how to pack their items to the backpack in order that backpack will have the least amount of space left there. So any ideas on how to solve this problem? What can be their state? Yeah, we know that W large is less than, I don't know, 10 to the power 6, and n is less than like 10 to the power 5. And less than 10 to the power squared. So typically an knapsack problem is NP-complete, so it cannot be solved polynomially. But if we know that the size of the backpack is reasonable, then we can solve this problem. Like on the complexity, that depends on the weight of their knapsack. So any ideas on what the state can be?
Well, we want to choose some items, and some of them on a certain step, some of them will be already put into the backpack.
Mm-hmm.
So I guess the state should be something about that.
Okay, the first state is good. It is like their I is the number of weights that we already considered. And right now we are trying to put ith element in the backpack. But I said that we have a limit on the whole size of the backpack. So let us maintain in our dynamic programming the following. So the number of elements that we already considered, and I don't know, like omega, so dp is 2 if we can take some subset of first so that gk less than equal than I plus equals to omega. So kind of we want to check, can we get this weight by taking only elements up to I?
Do you mean I is the position or just number?
I is the ith element in this. So kind of we take the first I w's, and we want to consider whether it is possible to get exactly this value of the weight. The question is how to recalculate that. So suppose that we want to calculate dpi w, or not w, omega. From which state we could come here? There are only two states from which we can come. Like there. The transition from which states we can get here. Of course, like the first will be that we didn't take this element, so it can go from dp I minus 1. So kind of we took this element, so like previously it was dp I minus 1. But what will be the weight, the corresponding weight?
If we didn't take W, it would be the same.
Yeah, if we didn't take W, like it will be the same. But if we take this element,
then we should decrease W by
Yeah.
that rate.
so omega minus Wi. So these are two states that we can come from. So the algorithm then is pretty simple. So you consider for I equal 1 to n, for omega 1, 0, from 0 to W minus Wi. We check, oh, sorry, not like that. We want to check from the previous dpi w. If dp I minus 1 w, then dp I w equals to true, and if omega bigger than or equal than wi and dp I minus 1 omega minus wi, then dp I omega equals to true. So we just do exactly as we talked. So we iterate over all the elements, we add elements one by one, then you consider all the weights there, and if we can previously not take an element I, we can get omega, then given element I we can also get omega. And if omega is bigger than wi, this means that we can get rid of ith element and check if it is fine, then ours is also fine. Then obviously the question, so suppose we already calculated this we calculated this dynamic programming and how to calculate the answer. So the answer is how we should get elements in order to get the least amount of space left.
Actually, I'm still trying to understand the code. Is there a little w somewhere, because w and omega look
so this is omega. This is omega. This is omega. Here is omega. Here is omega. Here is wi. Here is wi.
Okay, and when we take the omega from 0 to the wi.
No, we say omega from 0 to w, like to the all.
Okay.
To the whole range.
Yes.
Does it make sense?
So we just put the true in the elements where.
So this is exactly as we talked. So we have state their ith element, like that we consider the prefix of the elements, and the weights. What is the weight we want to achieve? Okay. So the first condition, if we didn't take ith element, and we could get omega, then we could get omega using the first I elements also. If omega is bigger than wi, this means we check without the last element. That suppose we add element I. So we should decrease omega by Wi and check, can we get this weight? And if we can get, then we can get the weight dpi omega.
So to get the answer, we want to take the largest omega there is, which contains a true.
Yeah, so we should take dpn and consider the largest omega here. Yeah. Why dpn? Because this is like n elements that we consider it, so like we should consider it. Okay. Do you understand how to restore the answer if you need?
Well, I think we could also do the thing with the from, which we would put the previous state every time we just put the true.
Yeah, that's true. We can kind of, like, it's probably even simpler that we can have from also the boolean. So it is true in this case, and this is from IW, this is false. So what does it mean? It means that we take or did not take an element. And that's your can correspondingly restore the whole path, whether you took an element or not. Okay. The only problem with this solution can be that we should store the rectangular matrix. There is a possibility to have only one array, but without the possibility to restoration. So we could get rid of the first and just calculate dp omega. That's pretty interesting because it is simply so if dp of omega is already true, then we don't need to have done anything. But if it is but again we could there are two options. Either you take the ith element or you didn't take. If you didn't take, dp omega will already be fine because it was true and afterwards it becomes true. Otherwise, if omega bigger than wi and dp omega minus wi, then dp omega equals to true. There is a small question, like this code will not work, unfortunately. It needs to be done a special trick to make this problem solvable using this algorithm. So can you tell me why this algorithm will be incorrect?
I have a question. Why do we check for the omega is if omega is greater than wi? So
no, this is because we have to decrease omega by wi. We should check whether we hadn't take the summon. So this condition is fine.
Okay.
But there is still a problem in this algorithm. The question is, are we sure that we can add element only once?
Well, I guess not. If we
So yeah, so suppose that we know that, I don't know, that 1 is true, okay? And we have an element of weight 2. So we come to 3, like we kind of 1, 2, 3, then we check. 3 minus 2 is true. Like we have the omega or Wi is equal to 2. So if 1 is true, then 3 is also true. Then you go to 4, you go to 5, you see 5 minus 2 is also true. So it will add true here, but this would mean that we add this element 2 times, which is impossible. So how do you think how we can change an algorithm in order to solve this problem?
Well, it seems like for each position we should store something that tells which elements we already used, but I guess that makes the rectangular matrix again.
Yeah. This is exactly why there were no such problem in the rectangular matrix, because you always take it from the previous line, from the I minus 1. Right now we don't have, like, the solution to that is simple. We just reverse this loop. And that's it. Since we are going from right to the left, we always ask the previous state and we never ask the next state. So kind of we can go from the true state only once. So that's the main trick that we use here. However, there is such problems where we have the infinite amount of these elements, then your algorithm will simply be as it was here. Like suppose we had infinite amount of items of the weight Wi, then if you have infinite, then we can go like that way and it will be automatically done because we will insert each element like a numerous number of times. So this depends on the problem. If you want the original knapsack problem, then you have to reverse it. Otherwise, you are good with that. Okay. But this is kinda very simple. Oh yeah, what is the complexity of the algorithm?
Be O of the big W, I guess, or multiplied by it.
Yeah, and multiplied by big W. Yeah, exactly. So typically the problem is a little bit different, so like you should be able to understand how to solve it in a similar manner that we have with weight. We have the cost of an element. So right now the question is, we can take one element one time, and how to get the most expensive backpack possible. So we want to take such an element so that they will fit into their knapsack or backpack, but with this total maximum cost.
Well, perhaps we should also store something like the maximum state, the maximum cost for our omegas.
Yeah. So instead of true here, we'll maintain the maximal possible cost with this parameter. Then all the recalculations will still remain the same. So their dynamic programming will be still the same. But instead of true, there will be taken the maximum of the previous state on this one. Okay. Okay, good. Now we know what to do if the total weight of the knapsack is limited by some reasonable amount. Oh yeah, the question is how to get an answer in the previous problem where we have costs.
Yeah, I think we should find not the maximum index, but the maximum cost that we get in the end.
Yeah. So we, instead of maximum index, find the maximum cost. Okay. Now let's suppose that W can be large, like 10 to the power of 18 or something like that. But at the same time, the number of elements is less than 20. What is good with these conditions? With this condition, like we know that the number of elements is small, so we can run over all their subsets to check that. How to do that? So we go for let me write this in C++, so like that, in kind of C++. So we consider the mask. Mask will mean which elements will be in there. So dp of mask okay, fine. 2, 1, shift n. So we iterate over all the masks till the 2 in the power of n. Then you iterate over all the items 1 to n. Like it will be from 0 to n minus 1. And if mask and I equals to 1, like what does it mean? Like the mask is zeros and ones where we take an element. We consider this element. And what does it mean? We consider if the ith element is taken. So like we take 2 in the power of I and end with the mask. So like it's a little bit like bit things, but it's better to know them. So and we consider as dp mask equals to maximum of dp mask and dp mask minus 1i plus ci. Oh yeah, at first also, yeah, I mean that's fine, but also you have to calculate for each mask the total weight of this mask. So there will be if mask, oh sorry, like it is the same, it is weight of mask plus equal weight of I. So we have two things calculating at the same time. For each mask, we calculate what is the cost of this mask. Like this is the cost. The maximal cost that we can get. Oh, sorry, no. I'm doing something strange here. Yeah, we don't need anything like that. It's much more complicated than I overcomplicate. So we have cost. We have cost plus equal to CI. And then we can get over all, oh yeah, and finally, like we calculated here, and if cost of mask bigger than current answer and the weight of the mask is less than big W, then ans equals to cost mask. So what we're doing, we just go over all the subsets, all the possible subsets. We calculate for each subset its cost and its weight. And if the cost is better and the weight fits into W, then we could change our answer to be the cost of the corresponding set. So is it clear?
Yes.
Okay, great. We can do a little bit better, and I'm like, oh yeah, what is the complexity of this algorithm?
Well, it should be 2 to the power of n multiplied by the n.
Yeah, so the complexity is like that. Now, suppose that we increase the number of elements. So like n equals to 10, this will fit into 2 seconds or so. But we want to do a little bit larger problem. So suppose that we have 40 elements right now. This will be a little bit more complicated. This algorithm is named meet in the middle. What we will do? We will take all these elements and split onto 2 subsets. So we will have W1, C1, Wn over 2, Cn over 2, and Wn over 2 plus 1, Cn over 2 plus 1, and etc. until and Cn. And let us build two arrays out of them. The sorted array, which will contain the mask and its weight. Okay, so how to do that? We already know how to calculate the weight of the mask. We know how to calculate the cost of the mask. Yeah, so this here is cost mask also. We also calculated cost mask. And then we know how to do that in n over 2, n times 2 in the power n over 2. We know how to do that because each part are n over 2, not n. So this is faster in squared time. And we sort them by the weight. Let us sort them by the weight. So this weight is less than this, etc. And we are doing the same here. What we want to do, we want to take one subset from here, one subset from here, add them together, so their weight is not higher than W with the maximal cost. So, does it give you an intuition how to do that?
By the subset, do you mean a single element or?
No, I mean the subset. So like this, like we have these are the subsets sorted by their weight.
Yes.
And these are the subsets of these guys sorted by their weight. So what we want to do, we want to take one subset from here, like the left part, one subset from here, and it will be our set together. This one plus this one should be together and should be less than W. So I think you should understand why I sorted them by the W. Any ideas why I did that?
Well, for example, if you want to take the minimum possible weight, we could just take the first elements, but we also want to maximize the cost.
Okay, so let us consider the first element here, okay? So it has weight 0. Which elements will satisfy us from here?
Everything that is smaller than the big W minus.
Yeah, so we could consider all these elements from here, big W minus W0. And which element should we take if we consider?
With the maximum cost?
With the maximal cost, okay. So then we move to W1. Which elements we should consider? We should consider all the elements that lie somewhere here. Okay? And so on. You go here by each element, and your set here will shrink. So this is exactly the two-pointer thing. So we have one pointer here, and we have one pointer here. And let us calculate for each of the prefix here the maximal cost. Because like what are our questions? We want to take W0 and to take their maximal cost on this prefix. Then you take W minus W1, you have smaller but it is still prefix, and so on. So if you calculate the prefix of the maximum of the prefix, then you can simply go using two pointers and to calculate their, like for each here we could calculate their maximal corresponding pair on the right. So that's it. You kind of iterate over all and take the maximum over all these maximums.
And how do we calculate the maximum of the prefixes? We just sum them, or?
Yeah, we just what we're doing, like we know this array, so we can go simply from top to bottom and calculate the maximum of max ans, like, okay, ci equals max ci minus 1. Oh, sorry. Yeah, mi is maximum of mi minus 1 and ci. So nothing non-trivial here. Just go down and add in one more element and consider the maximum the prefix.
Okay.
Okay, so this improved our asymptotics further. So now we can have in n times 2 in the power n over 2. Why so? Because the sort algorithm will work like these are 2 in the power n over 2 things, and the algorithm will like work sorting algorithm like that in running time like that. But it is indeed n over 2 times 2 in n over 2. So the sorting algorithm will give also this complexity. So we can solve the same problem with higher number of elements, but with the almost the same complexity.
So, if the number of elements is greater, should we do like recursive?
No, this doesn't work unfortunately. Like there is no way how to increase more. So this is meet in the middle. This is exactly kind of we solve one half, we solve another half, and we kind of want to merge them together. Like you work from one point from the second point. Merge together. This thing is named meet in the middle, and unfortunately, when you have 3 parts, they kind of don't have middle there. Okay. The next problem is also in the knapsack problem, but a little bit different. So you again are given items, and you know that you have a backpack with you have several backpacks with the weight W. And the question is, what is the smallest number of backpacks we need to fit all these elements? It's kind of a little bit different problem.
The big W is...
The big W is the capacity of each knapsack. Again, n is small, so n is kind of reasonable. It's even less, it's 15. So let me give you how we will solve that. So the first solution that comes to mind is just we came for all the masks from 1 to 1n. And we consider so we again we already have the weight of the mask, so we already calculated the array that calculates for each the subset their weight, and you iterate over all the masks that lies inside their previous one. So kind of we iterate over all the subsets, and we want to know their subsets that corresponded to the last knapsack we added. if mask and mask2 equals to mask2, then we can say that and the weight of mask2 is less than equal than big W. Then we can say then dp of mask equals minimum of dp of mask and dp of mask minus mask 2 plus 1. So what we're doing here, we iterate over all the possible subsets, and we iterate over all the possible subsets of the last knapsack that we filled with. So this guy is the second knapsack. Oh, not the second, it's the last knapsack. So that is why we consider if this mask, like this subset, lies in the original subset, and if its weight is less than W, this means that we can feed these elements into the knapsack. So we write dp mask equals to either the dp of mask or without this last knapsack.
Could you repeat how do we put the items? What is the last knapsack?
So okay, so you have like several knapsacks, and we kind of will be filling it using the masks. So kind of we put masks, mask 1 here, mask 2 here, mask 3 here, mask 4 here. So these are masks, to be honest, they're subsets. So exactly, and what we're doing, we kind of let us take the elements that weren't yet taken. So we take their 1 and minus 1 and take these masks out, mask 1, mask 4. This will give us the set of the remaining elements. And out of the set of the remaining elements, we take some subset, which should have the weight less than W, and we can add it here, like mask 5. So this is this like stupidest algorithm possible. You just choose the subset and add it as a new knapsack.
Okay, so we increase the number of knapsacks?
Yeah, so that is why here, dp of mask plus 1.
Yes.
Plus 1 here, so like we increased by 1. Does it make sense?
Yes.
Okay, great. What is the complexity of this stupid solution?
Well, it should be the 2 to the power of n squared.
Yeah, 2 in the power of n squared. So it is like, so this is all of 4 in the power of n. Great. I will explain now how to reduce it to the 3 into the power of n. It will be a little bit tricky. So is there a way of how to iterate over only the subsets of mask? So because here we just iterated over all the possible subsets and check if it lies inside the subset mask. So we want to iterate, like right now, iterate only over the possible subsets. So how to do that? I will write this in C style. So if mask, and then for mask 2 equals mask bigger than 0, and mask2 equals to mask2 minus 1 and mask. Suddenly, this passes only only the subsets. Why so? It's because we decrease by 1 and end it with the mask. So all the mask2 subsets, or all the mask2s are subsets of mask, because we take here and. Yeah, I mean, it can be simply shown also that we iterate over all the subsets, because we just decrease only by 1 and add the mask, so it will get through all the possible masks. Okay.
Actually,
yeah.
I'm thinking about the update. Don't we iterate through all the subsets again? If we decrease the mask by 1 each time. Oh.
Yeah. So how this looks like? So for example, we have 1 0 1 0 is their mask, and we have 1 0 0 is mask2. Okay. So it is the subset. So what we are doing, we decrease it by 1. And we set this one to 0, and all these guys becomes 1. Then you make AND with them, and this guy becomes 0. So you get exactly the same, or the next mask, if you consider only these bits.
Okay. Okay. Yes.
And it is why we iterate over all. So I claim that the work of this algorithm is 3 in the power of n. Why so? Suppose right now, like, we will set 0 if we didn't take an element at all. Didn't take 1 if it was taken in a mask and not mask 2. And 2 it is taken in mask 2. So kind of we take the set mask and we take the subset mask 2 out of that. So and any third digit number will give you the mask and mask 2, obviously. Like
What do you mean third digit?
Like you have something like that. Your state, kind of like the number of these iterations. Suppose that it corresponds to this 3-digit number. This is 3-digit number because we have 0, 1, and 2. So what does it mean? It means that their mask will be the guy with non-zeros. So 1, 1, 1, 0, 1. And their submask, which is mask 2, will be the guy with only 2s. So this will be mask, this will be mask 2. So, and we can encode each pair of mask and mask 2 into their 3-digit number of length n. Does it make sense?
So this number, is it a single iteration?
Yeah. So we want, like, what we want to calculate. We want to calculate how many times this iteration is called. This means like how many pairs of mask and its submask. How many pairs in total? I claim that this number of pairs is 3 in the power of n. What I do, how I prove that? I say that I can, for each pair of mask and mask tone, I can uniquely like make a bijection between them and some 3-digit number of length n.
Okay. Oh yes, I get it. Oh, yes.
So here I make the here I make a bijection. If I have 0, 1, 2, 2, 0, 1, the 2's are a subset and 1's are the set itself. And vice versa. If you have set that and subset here, you just add like 1's to the corresponding states of the subsets and get the 3, like to a 3-digit number.
Yes. Actually, it's a sum of those numbers.
Yeah, it can be looked at as the sum. Yeah. So, and since the number of such guys is 3 in the power of n, this means that the total number of pairs is 3 in the power of n. And that is why the algorithm works faster. Okay. But it appears that we can improve this further. So now we should make an interesting dynamic programming trick. So we will again have dp of mask, but now our dp of mask will, like previously dp of mask was what is the maximal number or the minimal number of knapsacks we need. Like let us consider the idea that you told yesterday about like let us add one, like this is quite similar to the tag problem that we had. Kind of we had the line and we fill the whole line with the elements. So like exactly as here we fill all the knapsack as the first time. But what if we add elements one by one? So we can improve the dp of mask is equal to the minimal number of knapsacks and the minimal weight in the last knapsack. So kind of this means that this knapsack's already full and we have some unfilled knapsack. So we kind of we add one by one element, and in some situation you have like this knapsacks that already filled, and you have some open knapsack to which you can add a new element.
Are they filled completely, or there's some space left?
Yeah, they're filled they're filled. Like you stop there. You will not add any elements there.
So the sum of the weights of the elements there is equal to the...
No, not equal. It can be less than W, but we don't care, really, because if, for example, like suppose that some of them are empty, like a little bit empty, and we want to add the future element here. Why wouldn't we add this element kind of earlier? There, like this will be the same. We can add this element earlier here to fill this gap.
So at each step we can put any element there.
Yeah, we can put any element. we can put any element in their open knapsack. So we kind of, and what we want to improve. So suppose that we take this subset of elements, we take this set of elements. Then what is the reasonable thing that we want to minimize? Like at first we want to minimize the total number of knapsacks, because this is our target function. But at the same time we want to minimize, like we want to get at most, like with the fixed number of knapsacks, we want to have the most space in addition that we have. So we want to have like the smallest number of knapsacks, and indeed out of this we want to know that the last knapsack will be filled the least to add a new element. So we kind of maintain this one, and you add like, so it will be simple, like for mask from 1 to 1 to the power of n minus 1. We will go for all the elements if mask and 1 is equals to 0. This means that this element is not in the mask, so we kind of add a new element there. Then dp of mask plus, so we consider, so we take their number of knapsacks and their space here. The filled space is as dp mask. Then we check if s plus wi is less than w, so we can add this element to the last knapsack. If we can, then we just say s plus equals to wi, else we should create a new knapsack with only this element. So like you say k equals k plus 1 and s equals to wi. And then finally you have dp of mask plus this new element equals mean of this dp mask and pair ks. So what we are doing here, we iterate over all the masks. We know that we already calculated the value for this mask. Then we iterate over all the elements that are left that are not inside this set, and we can add it. So if we can add it, we just get the total number of like the minimal number of knapsacks and the minimal space for this mask. And we want to add a new element. This element either fits into the last knapsack, so we have this condition, or we should create a new knapsack with the last space here. And we minimize, we take the minimum out of this two. Does it make sense? Okay, and you can see that the complexity of this will be n times 2 in the power of n. So we took the slowest approach 4 in the power of n and get the faster approach n times 2 in the power of n, which is indeed faster.
Is s the amount of space left in the last knapsack there?
Yeah, s, like this is k and this is s.
So is the number of space taken?
Is the number of space taken, yeah. Let it be like that. Not that is empty, but it is taken. So kind of we want to minimize k, and out of all the k's we want to minimize the how many elements in the last one. So I mean this tricky idea can sometimes appear on dynamic programming problems, where you want to minimize one thing, and instead of adding like lots of elements, you can consider it by adding one element. So like this, that like changes the algorithm a little bit. Okay, so this is knapsack problem. We consider different problems here. We have knapsack, normal knapsack, then we consider the knapsack with the minimal number of knapsacks that we need. So I think we are kind of done with the knapsack. So any questions to this point? Okay, great. So I think then we will stop it today. Thank you very much for coming.